Okay, now we are going to go. So this is section 5.2. Just as a reminder, all of the energy that's going on in a system, a reaction, all of those changes include both heat and work. We're just kind of ignoring work for our chemical systems, assuming that we don't have gases that are changing the pressure right now. So we're just focusing on what Q is. Okay, so what is calorimetry? Calorimetry uses the specific heat capacity of a material. We'll talk about this definition if you want to write it down again. The heat, which is Q, needed to change the temperature of a material per gram. And the specific part is the per gram. Sometimes you will hear people just call this the specific heat rather than the specific heat capacity. It means the same thing. We said that for water, the calorie was defined in terms of its 1 calorie to raise the temperature of water by 1 degree. So that relates back to our food calories. A food calorie, is it exactly equal to one of these calories? No, there's 1,000 of these calories in 1 food calorie. And this is an intensive property because it doesn't matter how much water you have, it's always going to be 1 calorie. And if I have a different substance, it doesn't matter how much that substance is, it would always be that specific. All right, so here we have a table of some specific heat capacities broken up into different things. I handed this out to you, right? You all have a copy of this? Okay, so even though they're really small up there, you should be able to see them on your piece of paper. So elements, most of those elements are metals, and that's consistent with the periodic table. So we got aluminum, iron, gold, graphite, carbon is a nonmetal, but all of these have a heat capacity that is less than 1. Now, what did we say the heat capacity of water was? 1 calorie. Here we're measuring in joules. So let's look at water. It's the first compound. What is water's heat capacity? 4, right? 4.184. So most of these elements, at least a quarter of the water, or less than a quarter. So water has a pretty high heat capacity compared to these pure elements. Now, it's not the highest of anything, but it is really high, okay? If we look at ethyl alcohol, ethylene glycol, they're not as high as water, but they are higher than these other substances. So key thing to notice on those is that at the end of the formula for both of those, you have an OH, okay? So the OH is what's called an alcohol group, and it's very similar to water because water has an H connected to an O, which is also connected to an H, okay? Those have what is called hydrogen bonding, and hydrogen bonding in chemicals increases the heat capacity because it's an extra attraction, and that extra attraction means that they're going to be tugging on the other molecules a little bit more. It increases the heat capacity. And if we compare that to carbon tetrachloride, the last compound there has no oxygen, no hydrogen in it, and now that compound's back down where all of the other elements were, okay? We have some solid materials. Again, these are approximations because it's going to depend on what kind of wood. Are we talking a soft wood or a hard wood? Are we talking dry wood or wood that is fresh and green and has water in it? If we're looking at steel, or we're looking with something with high nickel in it, or we're looking at something with high carbon in it. So those little changes are going to change what the heat capacity of that material would be. But we can make some approximations that that steel is going to be in a general area. Now, steel is mostly what element? Does anybody know? So it's over 90% iron. So if we look at the heat capacity for steel, it's 0.45. And then look up at the top, what's the heat capacity for iron? Also 0.45. Now we have it a little bit more precisely for the iron, but since it's mostly iron, the steel is going to be in that same ballpark. Okay, So let's take a look at how we would do a calculation with this. How much heat is given off by 18.3 grams of iron going from 91.0 degrees Celsius to 37 degrees Celsius? Okay, so we want to know what is the heat given off. So we're going to use that equation, Q equals MC delta T. So at this point, I'm going to switch to the chalkboard where I got this problem written up. Okay, and we're using Q equals MC delta T here. Okay, so the mass is that 18.3 grams. C is the heat capacity. Now it's really tempting to just always go back to 4.184, but here we're talking about the iron. So we need to look up the heat capacity of iron. So you got that on the table there. What's the heat capacity of iron? 0.450, right? And heat capacity on your table is in joules per gram Kelvin. And I've written it in joules per gram degrees Celsius. So I prefer to write it in Celsius, but we're looking at a change in temperature. If something changes by 3 degrees Celsius, it is also changing by 3 Kelvin. That amount is the same, right? So we just add when we're changing from Celsius to Kelvin, we don't multiply it by anything. So going from 0 degrees to 25 degrees Celsius is still a 25 degree temperature change when I'm going from 273 Kelvin to 298 Kelvin, okay? If you want to change all your temperatures to Kelvin, you can. But I find people tend to make the mistake of either only changing one temperature or waiting until they have the difference in changing the temperature, which is wrong because then you're making that temperature change a lot bigger than it is. So I think it's a better idea to just leave it in Celsius and tell yourself in your head, okay, yeah, the size is the same. Which is weird because in the last chapter, we were like all about, no, it's got to be Kelvin, got to be Kelvin, got to be Kelvin. So if it's a gas, we're going to do Kelvin. If it's calorimetry, we're going to do Celsius. Okay, so which one is going to come first for our temperature? We've got a 37 and a 91. The 37, because we do final minus initial. Now, the order of this matters because mass has to be positive. Heat capacity has to be positive. And the reason it has to be positive is what that says is I put in heat, something gets warmer. If it were negative, that would be saying I put in heat and it gets colder, which makes no sense, right? So these have to be positive. So the sign of Q, whether Q is positive or negative, is entirely controlled by did the temperature go up or down. So it matters what order you put these in. All right, so this is about 54. Try plugging that into a calculator, see what you get. So if you do 37 minus 91, it'll be negative. Yes. Okay, negative 444.56-ish. Yeah, so we round up that last digit, right? So 445. Okay, 3 sig figs, 3 sig figs, 3 sig figs. And that's the answer to that. That's just how much heat the iron gave off. Now, if we consider that the system and we consider the water, the surroundings, we might ask ourselves, okay, let's take this iron as it's cooling off, we're putting it into water. And so that water is going to be absorbing the heat because the final temperature was 37. So we do final minus initial. Good question. All right, so we have our water, 155 grams, and it's going to absorb all of this energy. We're just assuming it doesn't go anywhere else. We don't lose it to the air or to the container or anything. And it has an initial temperature of 22.5 degrees. And so it's going to get warmer as the iron is cooling down. Now, if this is our system and water is our surroundings, what can we say about the heat of the water? Do we know how big it is? So remember our Q of the system and Q of the surroundings are equal in size, right? So it's going to be 445 joules, but opposite in sign. So since this is negative, this one is positive. Okay, so that tells us this gave off the heat and the water absorbed the heat. Okay. Then we set it equal to our equation. So the mass was 155 grams. And the heat capacity of water, you'll probably have this memorized, but I will always provide it for you. 4.184 joules per gram degree Celsius. And we know the initial temperature, but we don't know what the final temperature is. So I'm just going to put TF here, whatever it lands at, minus 22.5 degrees Celsius. All right, so it's been a minute since many of you have had algebra. So remember, when we are solving these things, we got to treat the multiplication part a little bit different from the adding part. So I'm not going to be dividing by this 22, okay? This is within a parentheses. So I'm going to divide off the other part. So divide both sides by 155 grams and 4.184 joules per gram degree Celsius. That's going to cancel on this side. And what's going to end up happening is my grams here cancels, the joules cancel, and then this degree Celsius, it's underneath this division, the fraction for the units, but it's also on the bottom of the larger fraction. So being on under two fractions makes it on top. Okay, so whatever I come up with is going to be in degrees Celsius. Yes. And that's the right number of sig figs too, because we have 3 sig figs here. So it's 0.686 degrees Celsius. Now, when I look over here, I only have one number past the decimal here. So even though I have 3 sig figs over there, really I can only do 0.7. Okay, so let's think about this. If the water is absorbing the temperature or absorbing the heat, is the temperature of the water going up or is the temperature of the water going down? It should be going up. So I'm going to have 22.5 plus 0.7. So I'm going to add basically 0.7 to both sides. And my final temperature, or actually I'll add the 22 to both sides. My final temperature will be 23.2 degrees Celsius. I rounded this to one place past the decimal, because I only have one place past the decimal here. Or you can think of it as 22.5 plus 0.686. Add that together. What's that? 186. And then our rounding rules say I have to round to this digit, which gives me 22.2. Either way. Okay, so notice this temperature change was really, really small. This went 54 degrees and this only went 0.7. Okay. Two reasons for that. Can you think of one reason why it would be so much smaller for the water compared to the iron? One we talked about when we did. Heat capacity. Yeah. The heat capacity here is 4. So it takes a lot more heat to change the temperature of the water than it does to change the temperature of the iron. So that's a big part of it. Okay, so this is about 1/10 of this. Okay. The other thing is the mass. We only have about 18 grams here, almost 10 times as much of the water. So that heat is being distributed through a lot more material. If I drop that chunk of iron into, instead of, that's about 2/3 of a cup, if I put that into a gallon of water, hardly notice any temperature change at all. You might not notice any temperature change, okay? If you put it into a bathtub of water, you definitely wouldn't notice a temperature change. Okay, so this calculation is calorimetry. You're going to have at least one question on your quiz where you're going to have to plug something into Q equals MC delta T. Okay, so calorimetry is the method of finding these temperature changes. A calorimeter is going to be an insulated container. Okay. So I showed you the picture of the coffee cup calorimeter. We'll look at another one of those in just a minute. And then I'm going to show you a bomb calorimeter. Now, coffee cup calorimeters are considered to be constant pressure because we're just doing it out in the open. It has air pressure. A bomb calorimeter is going to be inside an enclosed area. Right? So stop this share for a second and bring this over here and borrow the corner of your desk. All right. This black box here is a bomb calorimeter. Okay. It doesn't really have explosions involved in it, but it's a container with a lot of water in it. And inside, there's a place where you can put a sample and you're basically going to light it on fire. So 2 electrodes go down in the top and they have a little spark, and then you're going to light that on fire, and then you're going to measure the temperature change in that water there. Now, this is a lot more than 2/3 of a cup. So we would imagine that temperature change would be pretty small, even if we're setting something on fire. So we have this thermometer. One of my students a few years back broke it, so we don't have the bottom part of it anymore. But this goes from 19 degrees Celsius at the bottom to 25 at the top. This is a 6-degree temperature difference. So most thermometers that you might have seen in lab are more like 100 degrees difference. So that means each of these little lines here is going to allow us to have 3 numbers past the decimal. So we can have a very, very precise temperature change. Compared to the thermometers, the digital thermometers that we use in lab, you only get 1 number past the decimal. So very, very precise. All right, so I will mention this again, but normally we just assume that the heat stays with the reaction, so the water that's in the reaction. And we don't really measure the amount that is absorbed by the calorimeter. So we assume it is negligible or near zero. That is not always the case. In lab, either you will measure that difference or you will be told that difference and how to calculate that in. Okay, so some close-up pictures. We still copying this? You all look like you're ready. I'll wait. Okay, so this is the inside of that bomb calorimeter. So I told you there were like 2 holes in the top where the electrodes go in, and the container that's in there is actually quite a bit smaller than that. That makes it look really huge. And then you have a stirrer that stirs the water around it, and that's how you measure the temperature change. Because this is not at constant pressure, it's technically not measuring enthalpy. So it's measuring heat, but it's not measuring the enthalpy, which is what we usually want to get to. And that makes the math a lot more complicated. We won't be dealing with bomb calorimeters. We will be dealing with coffee cup calorimeters. So you can see it's just 2 nested styrofoam cups. So foam is a really good insulator. But if you've ever had a hot drink, whether in a styrofoam cup or a paper cup with a sleeve on it, you can still feel the warmth of that. Like it's insulated enough that it's not going to burn you, but you can still feel that it's warm. So we have the second one to make sure that that heat stays inside the cup. A lot of heat can be released into the surroundings through the top. So a lid is really important, especially if you have large temperature changes. If you have small temperature changes, not so much. But if you have a large temperature change, that's really important. So having that lid on is why you wear a hat in the winter, because your head, that's where the heat is getting out. And then you have a stir. And you can see down at the bottom there, we've got a little solid. One of the things that you will do in lab is have a chunk of metal, and you are going to measure the temperature change, just like we described with this last problem. And so that would be that piece of metal sitting at the bottom of the styrofoam cup. So that's basically what your lab setup is going to look like. You may or may not have a stir. If you don't, you're going to use the thermometer to very gently stir. The problem with using the thermometer is that you might poke a hole in your styrofoam cup. So Just gently, don't stab, stir. Okay, so here we got our styrofoam cup. If we have a system that's solid, it's kind of hard to stick a thermometer in there. If we have a chemical reaction, it's kind of hard to tell what's going on with the chemical reaction. So we use the surroundings, and that's the whole point of calorimetry. So the calorimeter is designed to contain and measure all of the heat. And we're going to assume that the water absorbs the vast majority of the heat. Now, in class, that's always going to be the assumption, that the calorimeter isn't absorbing anything. I will show you next week how to account for the calorimeter, but today we're just going to assume all of that heat went into the water. There's no difference. So clearly the thermometer had to absorb something, otherwise it wouldn't have a temperature change. But again, we're going to assume no absorption there. And always this is going to come back to the heat from the surroundings, the water, is the opposite of the heat change of the system, whether it's going in or coming out. And that is derived from the first law of thermodynamics that says, can't have energy changes in the universe, so whatever's happening in one place has to be the opposite of everything else in the universe. Oh yeah, and in this particular case, Q of the water is the opposite of Q of the sample. Okay, so we are going to do an example here. We are going to consider our coffee, our system. And a lot of times you get coffee and it is super hot, too hot to drink. So at 75 degrees Celsius, that would cause a burn. We don't want to burn ourselves. Okay? So we think to ourselves, well, water absorbs a lot of heat. If I just add some room temperature water, maybe I can cool it down. So we're going to add water at 18 degrees Celsius. Comes out of the tap a little cooler than the room is usually. And we want it to cool it down to 58 degrees. So this is still going to be hot to us, but it's not going to burn us. And we want to know what is the mass of the water that we need. Okay, so we need to separate our system and our surroundings because we've got information about both of them. So our system is the coffee and the surroundings is the water. Now, if we had named them in the other direction, it wouldn't matter. The math would still work out. So we know we have 180 grams of water. For the heat capacity, we're going to assume since the coffee is also made up of water, that it's going to be 4.184. Okay? But we do have to pay attention to what is the substance. So since coffee is mostly water, that'll work. So heat capacity is 4.184. The final temperature that we want is going to be 58, and the initial temperature is 75. Okay, so that all we can plug into Q equals MC delta T. Got everything we need to make Q equals MC delta T. But what we want is the mass of the water. So what do we know about the water? We don't know the mass, but we do know the heat capacity. We know its initial temperature is going to be 18 degrees Celsius. And we know the final temperature that we want is 58. All right, so this is good. We've got lots of data and only one unknown. One unknown makes life much easier. Okay, so we're going to find Q for one side, the coffee. That's going to be MC delta T. And we just plug in those numbers. Now we put the 58 first because that's the final temperature. We want it to land at 58 degrees. So since we're getting close to the end of class time, I'm just going to go through the numbers, not going to have you plug it in. So I come up with 12,803, but I only get 2 sig figs. If I look at my temperature there, the difference between that is going to have 2 sig figs. So I'm going to round this to 1,300. And it's negative because the coffee's getting cooler. It's letting off that heat. So that's the Q of the coffee. What's Q of the water going to be? Going to be the same thing, right? Because it's the surroundings, but positive. So it'll be positive 1,300. Then I plug that in with the mass being my unknown. And after shuffling things around, I find it's 78 grams. Well, that's quite a bit of water compared to the amount of coffee that I have. It's almost half as much. It might be a better idea to use an ice cube. All right, I want to set up one more thing. We got what we need off of this page. All right, so this is similar to what you're going to be doing in lab. You won't know what your metal is. You're going to have like 4 possibilities, and you're going to be trying to figure out what is the heat capacity. But here I'm telling you it's iron. It has a certain mass, and it is heated to 98.2 degrees Celsius. So what you're going to do is you're going to put that metal in some boiling water, get it good and hot, so you have a big temperature change, and you're going to place it in some water. Water has the same temperature as the surroundings. And then we reach thermal equilibrium. What does thermal equilibrium mean? Thermal has to do with temperature. What does equilibrium mean? What do you think it means? Sound like it means? The system and the surroundings are the same temperature. So when the metal cools and the water raises and they equal one another, we're at 21.1 degrees Celsius. So you'll see thermal equilibrium in your lab. That's what that means. We remember that the water has this heat capacity. That is not the heat capacity of the iron. That's what we're solving for. So our goal is to find that specific heat capacity. So we're going to use Q equals MC delta T for the water. And our Q is going to be mass. So the mass of the water is what? The 10.78 or the 54.2? 54.2 times the specific heat capacity times the change in temperature. Notice my 21.1 comes first because that is the final temperature. And when I plug that in, I get 360 joules. So what is the heat for the iron? It's going to be the same number? Yes, but it's going to be negative. Okay, so the iron is negative 360. And I plug that into Q equals MC delta T. This time I'm solving for C. And I should end up with 0.43. Now, because we're making the assumption here that the calorimeter doesn't matter, your number's not going to be exactly what you find in the table. So you kind of have to take that into account. So that's basically your lab setup for next week. All right, any questions? All right, have a good weekend. Don't forget to study gas laws as well. And I will see you on Monday.